So, in the last lecture, I think it was lecture 23 or so, but um, we talked about the general equation for stress within a thick-walled cylinder, and we developed this relationship between our tangential stress and our radial stress using this differential equation. Um, and then we said if we took the derivative of this equation with respect to r, we got the equation on the below. Um, and then we were able to plug in these two values into another equation in order to solve for an ordinary differential equation, all in terms of sigma r that we have shown here. And this is the general differential equation for thick-walled cylinders. Okay, so using this equation, if we know the boundary conditions of the problem, we'll have a few different solutions to this ordinary differential equation. So the first case, which we talked about during the last lecture, was that if we had a rotational velocity equal to 0. So, and if you have omega is equal to 0, this term on the right hand side of this equation, it'll go down. It'll become, if omega is 0, this term will become 0, and we're left with this uh, differential equation here. Okay, and the solution to this differential equation was here was this equation 5.812, and then we know the relationship between um, uh, equation 5.8 dash 6. We can plug in sigma r into that equation in order to get sigma theta, and then we talked about if we had plane stress, we'd have or in a case where we have the length of the cylinder couldn't be ignored, we also would have our third principal stressor, sigma z. Okay, so so what this looks like in terms of a cylinder, if we had a cylinder, all right, it has an internal radius, it would have an outer radius, okay, it would have our thick-walled cylinder may have some rotation. In this case, we said it was equal to 0. All right. Then we had the we also had the external loads, so we could have our pressure, external pressure on the outside of our cylinder, and we could have the internal pressure within our cylinder. All right, and then um, the so if we took a small element out of our section, we would get a stress element that would have a radial stress, it would have a tangential stress, and then if we make it a 3D element, it could have a stress along the z-axis. Okay, so um, so um, so due to these stresses, due to the internal pressure and the external pressure, what you'll end up getting is you'll get some displacement. So you'll get some displacement in the radial direction due to these forces. So, um, basically the inner radius and the outer radius may increase or decrease depending on what sigma r and sigma theta are. So if we know what sigma theta and sigma r are, we go to the next page. Okay, we can plug in sigma theta. We can plug in sigma r, and we have to know what the elastic modulus and the Poisson's ratio are, and the radius at that point, and we can solve for the displacement. Okay, and if we had, in the case of two concentric cylinders, so if we have, in the case of two concentric disks, what we would have is we'd have an inner radius, which we'll label A, and then we have the outer radius of a cylinder, which we'll label that B. Then for our outer cylinder, it would have an inner radius of B, and it would have an outer radius of C. Okay, so the interference between these cylinders Alright, so if the inner radius of the outer cylinder is less than the outer radius of the inner cylinder, in order for these two cylinders to fit together, there needs to be an applied displacement. And that applied displacement is called the interference, which we'll denote with our delta term. And that delta term will cause an interference pressure that we'll label with a lowercase p. Alright, and that interference is a function of the displacement, the radius at the interface, and the material properties and dimensions of our two cylinders. So we have our outer cylinder and we have our inner cylinder. Dimensions and properties. So if we can take these both into account, we can then solve for the pressure between the two interfaces, and once we know the pressure between the two, we can then go back into our stress equations, and we can plug in the pressure into our sigma r equation or sigma theta equation for both the inner and the outer cylinder. All right. So in conclusion, that our original ordinary differential equation, if the disk is not spinning, the solution to it is very simple, and we can solve directly for sigma r and sigma theta. And if we know the pressures and the dimensions of our cylinder, and then in the case of an interference fit, it's pretty simple, straightforward to just solve for the if we know the dimensions of the inner cylinder and the outer cylinder, and we know the interference, and we have the material properties for both parts, we can solve for the pressure. So pretty simple in order to find our stresses and find our interference pressure.